All right, so we've been discussing the components associated with the MR system, the MRI system, and we talked about how you first of all have to have the main magnet. The next thing that you have to have is the coils or the coils that produce the field gradient. Now, this is not the main magnetic field, nor does it have the magnitude of the main magnetic field. The main magnetic field is there, it's a background field that polarizes the hydrogen atoms in the body. And then what happens is there is an RF field that's applied as a pulse field on top of that. And if you have a physics background, one way to think about this is that this RF frequency is tuned to a resonant frequency associated with the spin state within a hydrogen atom. So, um, if you don't know anything about physics and spin states, that's okay. But if you do, that gives you a little bit of background. So that sort of is what selects um, the characteristics of the RF field. Then it's it's imposed for a brief period of time. Um, it includes gradient coils for all three spatial directions, x, y, and z. It's a temporary field. They're switched on briefly, and the molecules, the hydrogen atoms, respond to that. They respond to this gradient field. How they respond and how long it takes them to recover after the field is switched off are part of what gives you the MRI image, because different types of tissue will have different time constants associated with them and different strengths of their response. So that's what gives you the actual MRI measurement itself, is looking at the different types of response to different types of stimuli. And there are a number of different RF sequences that involve both the excitation as well as the timing of when you make a measurement. So the instrumentation associated with the gradient system has to allow for a high degree of control, as does the instrumentation associated with the measurement system. Now, because these are big currents, up to 500 amperes, and they have to be switched with very great timing accuracy and high levels of stability. So because of that, internal forces are generated in just the mechanical system that provides this. And so because of that, that's why you hear these loud kind of knocking sounds during an MRI. The ones that you hear have actually already been attenuated, but they're still present. So it's actually not things in your brain knocking around like I've had people ask me in the past. It is mechanical forces causing a banging in the system. So the RF system consists of two things. It consists of a transmitter. Transmitter has to accurately send RF pulse sequences. These pulse sequences can vary in both center frequency and bandwidth. So the amplification on the RF transmitter has a preamplifier that generates the signal, and then a transmit amplifier that increases the signal gain as required. The receiver, this is a very weak MR signal. So when it comes out, the signal to noise ratio is very poor. What you're measuring is very small. You have to then amplify that in an extremely low noise amplifier before it's digitized and processed further. The better the signal, the stronger and clearer it's going to be received by the coil. And the signal strength depends on the volume that's excited in the receive coil and on the distance to the measurement object. So this is why sometimes you have additional coils that are inserted inside the magnet. If you're doing a brain MRI, there's something known as a head coil. It fits in very close proximity to the head, so that you deal with this distance issue um, and improve your signal to noise ratio. All right, so those are some of the main components, but I think one of the things that's important is to realize that there's an overall system level, there are overall system level things that have to be addressed with an MRI that go far beyond the magnet and the RF coils. And so I want to look just a little bit at this figure, which shows just a schematic. This person is having an MRI done on the knee and on the spine. And so this figure is illustrating several things. First of all, You can see that you have your main magnet in here, and that this is liquid helium cooled. And then you have so the main magnet's illustrated in red. Then you have your shims that are there to uh, control the homogeneity of the field in the bore, and they can be independently adjusted so that you have a homogeneous situation inside. Then you have some shielding that occurs to sort of keep the magnetic field contained and prevent leakage into the room of the very high magnetic field. It's overall in a shielded enclosure, and as I said, these are liquid helium cooled magnets. There is typically a system that is not shown that surrounds this whole system that is a liquid nitrogen based system. It pre-cools everything before this is brought down to liquid helium temperatures, and it also hopefully presents a completely catastrophic failure um, should the power be lost and liquid helium be released and the magnet come up to room temperature. It's important to note, as stated here in the notes, that once you get this high current in a superconducting environment, this will flow for years without requiring any voltage. So, what's taking up the energy in keeping an MRI system working is not running the magnet continually, but rather keeping the liquid helium cooled and generating and circulating cooled liquid helium. It's probably also worth pointing out that the MRI system, because of this reason, because it stays at high current and high field generation even when it's not being actually used, remains a safety issue. So, when entering an MRI room, even if an MRI is not actively being used to acquire data, one should always be aware that this magnetic field is there, that um, the main magnet is active, and so appropriate safety precautions should be taken. What are those? Um, Most MRI rooms have a metal detector so that if you try to enter the room, the door will not unlock if you're carrying metal. So there's an interlock system. You have to empty your pockets. You don't want any metal in your clothing. Fillings in your teeth and crowns and retainers are okay as a general rule, but you certainly don't want to be carrying, anything metal, keys. They can become deadly projectiles in the presence of the magnet. Also shown here are the RF coils, and then there are some shims for the RF as well. Shown here is one of these accessories that fits inside the magnet that provides the RF much closer to the source of what's being measured. So these are accessories that a person can buy um, that give you better resolution and better signal to noise because you're closer to the physical area being measured. Um, if you have an open MRI system, the best you can do, state of the art, with a clinical system in field is 1 Tesla. So, for that reason, the open MRIs don't give you quite the resolution that the closed MRIs do. But in a lot of cases, it may be better than no MRI if the patient is extremely claustrophobic and for whatever reason can't tolerate the system. So, here is a look at what the equipment room looks like. This would be the room adjacent to the magnet. Um, in this cabinet here are the gradient coil excitation sources and the associated RF equipment. Universal power supply is shown here. The water pump and chiller is shown here. The water pump is used to pre-cool even more and just to circulate cooling water throughout the entire facility because the RF coils get hot and other parts of the system get hot due to the RF. And then here's the helium pump. Helium needs to be recharged on a fairly frequent basis, and so typically you have a contract with the company that just comes and recharges your helium tank, which is typically located in a shielded environment, usually outside and away from the rest of the equipment. Here's a look inside the RF cabinet. You can see you have 1, 2, 3 different RF amplifiers for orientations X, Y, and Z. These black hoses contain a coolant that's circulated basically to remove the heat that's generated by these amplifiers. So this would be part of what your uh, water circulation cooling is being used for. No need to cool this down to superconducting temperatures because this is just to deal with thermal heating due to ohmic considerations. Here are some additional components of the cooling system. Here's a block diagram of a GE type system. It shows very similar arrangement. Here's the power gradient RF cabinet. Here's the heat exchanger cabinet. Let me go back, sorry. Here's the heat exchanger cabinet. Here's the cryo cooler compressor that's dealing with the helium. Um, and then the cooling circuitry for the main magnet and for the gradient coils. The helium pump is shown here. These are basically heavily insulated hoses that take the helium back and forth. There's a heat exchanger and chiller that pumps an antifreeze water mixture that's there to cool the gradient coils as well as take some of the heat away from the helium system overall. And then here's the external part of the system that deal with your main electrical and cooling equipment exterior, and usually the helium storage tanks are placed either inside these cabinets or in another special cabinet. So often the helium supplier can come and replenish your helium without disrupting anything if should it need to be replaced or replenished on a regular basis. They can just come in and they don't have to take the system offline or anything. There are interconnects built in. So you can see the engineering that goes into the MRI system involves a lot of mechanical engineering because there's quite a bit of piping, plumbing, heat exchange, cooling, etc. There are also quite a bit of electrical engineering considerations, the circuitry that controls the RF gradients. And then at this point, we haven't even really touched on the acquisition. So, how are the data acquired? How are the RF pulses determined and programmed? And how are the measurements analyzed? So, because that's not directly a medical instrumentation consideration, not really going to go over that in this class other than to say it is a major component of an MRI system.